Hello everybody, today is May 6th, it is 2020. It is our recorded lecture. It's week 16 of the spring 2020 semester, and this is class number 2. And I'm going to let you all know, as my first announcement, this will be our last recorded lecture. What I found is that this week is incredibly intense for people trying to finish up not only anything they're going to do in this class, but in their other classes. So what I'm going to do is this. I'm going to go through the materials I have for you today. There will be a participation for the week, as well as a participation quiz for today. So I'll have those consistent with everything else we've done this semester. But with regard to Friday's class, which we typically, again, would have 3 classes recorded, I'm not going to do that. Instead, what I'm going to do is I'm going to put out a review sheet for exam number 4. It's going to have a list of questions that pertains to material that folks can review if they plan on taking exam number 4, and then I'll post the answers as well so they can double check the concepts and any kind of calculations that they do. So that's the first thing. Second thing to mention is that with regard to exam number 4, we're going to go ahead and release that. I can't release it any earlier than next Monday. For finals week is just how it'll go, and you have the entire length of the week to take it. I know it says 50 questions on there. I'm going to reduce it to 40. I'm sorry, it says 50 points, but I'm going to reduce it to 40 just to keep it consistent with everything we've been doing. I think that was in kind of a beta mode or a test mode from previous, and I always kind of tinker with these things each summer, so I'll fix that. In the meantime, what I'll do is I'll be answering probably lots of emails like I've been doing. I want to encourage you guys to do extra credit if you haven't or if you need it, and also to finish your presentations. Those are the main things. So I think with announcements, those are the major pieces. It's been a pleasure. It's been difficult. It's been a difficult semester, but we, have made it this far. I think many people are doing quite well with respect to their understanding of the knowledge that we started with and are ending with now. So I'm very impressed with our class. I'm very impressed with the effort. And most of all, I'm impressed with everybody's ability to just adapt to an ongoing and very fluid and uncertain situation. And in a lot of ways, this mirrors what happens in social work to begin with. And it also gives us a taste of what a lot of our clients' lives can be like as well. A lot of uncertainty, a lot of risk, a lot of vulnerability. So I think that, again, this was terrible, and it's a learning process. This whole reaction to the pandemic is a learning process. So I think in that way we can find something positive. Nonetheless, I'm going to go ahead and start with ANOVA, the final piece. I'm going to do a little bit of review, and then the rest of the review is going to come in the form of questions which I'll post with answers following. Okay? All right, I will move on to ANOVA. Okay, everybody, so I was digging in my archives of ANOVA materials I have, and I found this wonderful review. You can see it starts out with ANOVA is a blank statistic, and it goes on. Let's go ahead and take a look at this. ANOVA is a blank statistic. The null hypothesis states there is no blank between the blank of the samples or populations. ANOVA is similar to blank statistical analysis. However, ANOVA applies exclusively when there are blank or more samples or populations. For ANOVA, we use a calculation which gives us a blank. For ANOVA, like other similar statistics, we compare the blank value to the blank value. Okay, so let's take a look at the first one rather. I guess they're not numbered. We'll go bullet number 1. ANOVA is you already know the answer, inferential statistic. So, inferential statistic. The null hypothesis states there is no difference between the averages of the samples or populations. ANOVA is similar to t-test statistical analysis. However, ANOVA applies exclusively when there are 3 or more samples or populations. For ANOVA, we use a calculation which gives us a F-score or F-value or F-ratio. Remember, there's lots of ways to say it, huh? Finally, for ANOVA, like other similar statistics, we compare the calculated value to the critical value. Okay, again, that hasn't changed at all. So there's our very brief review. We'll move on to the next one. Okay, application problem. I have these. A researcher wants to know if there's any difference in the average student suspension rates for 3 schools in a district. So right off the bat, we have a couple of things that we can identify this ANOVA by. So difference, averages, and 3 schools. So all the elements are there. We're looking for a difference, the difference among averages, and there are 3, not 2, okay, groups that we're looking at. Okay. To set up the study, the researcher interviews a teacher from grades 1 through 6 from each of the 3 schools. He then averaged the scores for each school and then applied ANOVA analysis. So we went in and talked to all of the teachers grades 1 through 6, found an average of the suspension rates. Okay, then we apply ANOVA analysis because we've got 3 averages to compare. Well, what do you think the null hypothesis would be for this study? Okay, give you a hint, there is no difference. Okay, the researcher recorded the results for each school, which is demonstrated on the following slide. So again, going back to the null hypothesis, don't forget again, null hypothesis, there is no difference, okay, among the suspension rate averages for the 3 schools studied. Okay, something to that effect would be the null hypothesis. Oops, it's not the one I wanted. Okay, so here's our grades 1 through 6. Okay, school 1, we have an average. School 2, we have an average. School 3, we have another average. Look at this. School 2 and school 3 have, looks like the same average, right? Okay. Well, here's our raw data. Okay. Going to square them like we do. Okay, again, there's no expectation I have for you to be able to do these kind of calculations. I'm just showing you what they look like. This will not be on a test. This will not be on a homework assignment. We're done with all of that. This is just me having some time to prepare you for a potential encounter with these in the future. So again, that's all I'm really doing right now. Okay, there's that same equation we use for this. Okay, mean square between, mean square within. Okay, that's the ratio, the F ratio. Okay. Yes, we've seen this one before. The mean squares and F ratio. Okay, F ratio basically is the mean squares between over the mean squares within. Okay, what's all this mean? Well, I just did this for you. Okay, you can see how I did it. Okay, I took the sum of squares between. Okay, came up with one particular number. Took the degree of freedom between, and then when we put that as a ratio. Okay, so we took the sum of squares divided by the degrees of freedom. Okay, there it is right there, the 2.8 over the 2. We have the numerator here for the ultimate equation. I know there's a lot of ratios and equations here. Same thing with the sum of squares within. Okay, sum of squares within. Okay, we found 398.1 degrees of freedom within. Okay, again, that gives us the denominator for our F ratio. Okay, very useful slide presentation. I'm glad I kind of found this. Okay, and then here's what it would ultimately look like if you were using an application like SPSS. Okay, again, here's the between. Okay, here's the within. Okay, here's the, remember when we were talking about the MS between, so there's the MS between, MS within. Okay, we have the numerator, we have the denominator. Here's our ratio. Okay, our F score. Here's the critical. Well, let me ask you, what looks bigger? Because I threw this in here. I love this slide because, frankly, I had forgotten about this presentation and found it. So it's like finding money in your pocket after you've done the laundry. Okay, you can see that the F score is a decimal, and you can see that the critical value is a whole number plus a decimal. We already know who's going to win that battle, the critical. Okay, so clearly the p-value is going to be greater than 0.05. Based on the findings, what should happen to the null? Well, you tell me. Okay, if the critical is greater than the calculated, the p is greater than 0.05, we have got to accept the null hypothesis. Okay, that's exactly what happened there. So I like that example. That was fun, actually. For me, I don't know if you enjoyed it, but again, this is another type of analysis that in the future, if you find yourself doing any kind of calculations where you are comparing averages of 3 or more groups, it's going to be much more advantageous for you to use an ANOVA than a t-test, because with the t-test, you're going to artificially inflate the p-values. So that's not something you want. You want to have a stable p-value, and the only way you're going to get that is with an ANOVA if you're comparing that many number of groups. Otherwise, you can run like 100 t-tests if you want, and then you're going to get this wild, I guess, parameter for what's an allowable p-value, and it's just not a very good way of calculating the numbers. So again, I love this problem. I think in future classes I'm going to use this one quite a bit, because I had completely forgotten about this slide and I found it. So again, very happy right now. Anyway, so I hope you enjoyed that. That's kind of I think for all intents and purposes, that's my last presentation to you of the semester. And again, maybe you can get something out of this. Hopefully you can. At a minimum, you will know going into the future what an ANOVA is and when to use it and how it operates. It operates like a t-test, only with greater numbers of samples. And also, to me, it's actually a very useful type of statistical analysis. It's clearly one of the more complex we have. It's conceptually complex, and even in terms of doing calculations, it's quite complex. But nonetheless, it's a fun one. I've always thought ANOVAs are fun, but anyway, that's me. I think things like that are fun, so you can scratch your head on that one, I guess. All right, so now we're going to move on to the review for those of you who are interested in doing exam number 4. So again, I'm sure I'll have a chance to say goodbye to you, each one of you individually at some point. And if not, just know it's been a pleasure to work with you guys this semester. And, for all those of you who are leaving right now and you don't have any interest in taking exam number 4, know that I think you're champions in going through all of this and weathering the storm through a very intense semester. So it hasn't been ideal, it hasn't been desirable, and at the same time, it's what we have. So keep on persevering, know your value. You have high value, and know that you can apply all of your strengths and skills and talents in the future for the profession of social work. Okay, and hopefully our paths will cross again. So I'm going to move on now to do the review, and if this is your last stop, then like I said, good luck. Otherwise, I'm not going to do any more recorded lectures. They're just, it's not necessary anymore. We've kind of hit the end of the path. And I'm going to go ahead and just post for Friday review questions for people who are going to be taking exam number 4. Okay, if you're still with me, then we're going to go through just a couple of items here, and the rest are going to come out in the form of questions. I'm going to be posting online eventually, probably beginning today all the way through Friday. Today is Wednesday, so we have a couple of days to go through review, which again, I don't suspect that I made the questions on the exam number 4 any harder than I would make them any other time. So I don't suspect you need a ton, just a little bit of touch up. Again, if things have gotten stale, we're just kind of reviewing them. So let's go ahead and jump in. So item number 1, frequency distributions. So I have something up for you that I'm going to show you here in a minute, just to remind you about what frequency distributions are, how they work, and things to remember about them. Okay, so remember I'm going to go ahead and pull this part up here. Remember that when we're talking about, hopefully you can see my little example here, we're talking about frequency distributions. We're talking about basically tables of data. We're putting them in order, so we're creating information. Remember, data is raw, whereas information is more processed. Here's where we have a number of people in a group. We have their ages, and we're trying to categorize them according to their age. So we have Chuck and Tony, and so I guess these are the people. Here are their ages, and what we're trying to do here is we're trying to organize them according to their ages. So how many people are at age 21? Well, Chuck and Tony. So there's 2 people. So we have a frequency of 2 for 21-year-olds. Okay. And now let's go down here. We have 3 people who are 26. So we have Brad, Herb, Karen. They're all 26. So we say 3. Okay. Rosina, Peter, Leon are all 27, so we have 3. Now, that's how you do the absolute. You have the absolute frequency is just the raw number of people at any particular attribute of a variable. So the variable is age, and the attributes are 21, 26, 27, all the way down to 69. So let's go ahead and take a look at this. So we have 2 people who are 21, 3 who are 26, 3 who are 27, 4 who are 31, so on and so forth. That's the absolute. Okay. Then we have the cumulative column for the frequencies. Remember how we did these? This is where I was talking about starting at the top with an elevator. As the elevator goes down, the values get on. So we start at the top where there's none. Okay, we come down here, there's 2 that get on. Okay, then the elevator goes down a floor, 3 get on. So what's 2 plus 3? Well, it's 5. Okay, so now we're hanging out at 5. When we go down to the next floor, 3 get on. Okay, 5 plus 3 equals 8. Okay, 8 goes down another floor, picks up 4. 8 plus 4 is 12, all the way down to our total N, which will be 20. So by the time we get to the bottom floor, every one of these frequencies should be accounted for. Okay? Let's take a look at the what we do in addition to frequencies. Remember that with frequency distributions, we not only do the frequencies, we actually also do the percentages. So here we are again. You can see this hopefully fairly clearly where my cursor is. I think I put the cursor highlight on, so you should be able to get a good idea. This isn't new to you. You saw this above. Okay. Here's the frequency, but then look at the percentage. So 2 of 20, because we know there's 20 total. 2 of 20 is 10%. Okay. So here's your percentages. 2 of 20 is 10%. 3 of 20 is 15%. 3 again of 20 is 15. 4 is 20. Now this should all add up to 100, shouldn't it? Well, that's good. These are the absolute percentages. So when it says absolute, it's pertaining to just that row. See, so 10% of the population is 21. Okay, 10% of the entire population is 21. Okay, 15% is 26. Okay, but then we move over to the cumulative, and that's that whole elevator thing again. Okay, it's like a shaft going down here. Up here we have nothing. We're on the roof. Okay, we go down, pick up 10, go down. Okay, 10 plus 15 is 25. Okay, go down, pick up another 15. So 25 plus 15 is 40. Okay, again, go down another level. 40 plus 20 is 60. Okay, so on and so forth until we get to it has to be 100 at the end. Okay, well, otherwise we're missing somebody. So that's how you do frequency distributions. Again, this is the thing you absolutely have to take home. Frequency distributions commonly include not only frequencies but also percentages, and they include both absolute and cumulative. So absolute would be the number specific to that row. Cumulative, just like your GPA, is when we're going through all of them. They're all adding up. Okay, hopefully that helped you. But again, this is just review. So that's we can check off frequency distribution. You know what those are now. Okay, now upper measures of central tendency. I think you recall what those are. Measures of central tendency are simply the mean, the median, and the mode. Okay, what do we mean by the mean? Mean is equal to the number of values. So if we have 2 plus 3 plus 4, okay, we're going to go ahead and take the total here, which again, 2 plus 3 plus 4 is going to give us 9, because 2 plus 3 is 5, plus 4 is 9. Okay, and we're just going to divide it by the number of values we have, 1, 2, 3. Okay, so if we're going to divide 9, which is the total value, okay, by the values we have 3 values here, 2, 3, and 4. So we're going to divide it by 3. Okay, and 9 divided by 3 is going to be 3. Okay, what's the median? Okay, the median will be the middlemost number. For our group up here, we have an odd number of values, so the median is going to be 3. Okay. However, if we had let's say it did look like this instead. Okay, what we would do is we would, so now we have an even number. We would take the middle two values, okay, and the middle two values right here would be 3 plus 4 is 7, and half is 7, okay, it's going to be 3.5. Okay, so you would find with even numbers, you're going to have to take the middle, you're going to have to add, you're basically going to have to take the mean of the two middle numbers. That's the easiest way to remember it. And then the median is going to be, of course, the middle number. Again, it's easy if it's odd. Okay, if it's even, you're just adding. Okay, the mode, okay, or the mob, as I like to call it. Let's just say that instead of these numbers we had, let's see, 3. Okay, let's say that this had been our set of numbers in the data set. It had been, I'll just get rid of this for you so it makes it less confusing. Let's say that this was our data set. Okay, well, mode is the most frequently occurring value. Which value is occurring more than others here? Well, clearly 3. So that's the mode. So those are the measures of central tendency. Very, very easy for us. Okay. let's take a very brief look at what we mean by measures of variability. The first thing to remember about measures of variability is that they go by a different name too, measures of dispersion. Okay, dispersion. What are we talking about when we're talking about measures of variability? We're talking about things by the standard deviation. Do you remember standard deviation? I'm not going to have you do any standard deviations on the final exam, on the exam number 4. You can maybe hear cats scratching in the background. That's not a good thing. I don't need furniture destroyed. So I'm going to ask these cats to please stop doing that. Okay, anyway, sorry, standard deviation is one. Okay, we're also talking about variance. Okay, range. Okay, it's the highest, subtract the lowest value in any data set is going to give us the range. Okay, standard deviation is basically the average distance. Okay. Okay, average distance between, let's spell it right, between data points in a data set and the mean. Okay, we did a lot of that at the beginning of the semester. I know it's been a while, but the only thing, the thing I need you to remember is basically this definition is it's the average distance between data points and the mean. Okay, variance is just going to be, I think you might recall that the variance is basically the same thing, except it doesn't have a square root in its equation. But again, I'm not going to be asking you any questions about variance. I might ask you a question about range, and if I do it, it's just going to be 1. And this is really the only thing you need to remember is the range is the highest value, subtract the lowest in any data set. So highest value, subtract lowest value, okay, in data set, in any data set, okay? That's the main thing to remember there in terms of measures of variability or dispersion, okay? So again, this is review. This is not hard. These are just little things we've covered in the past. You hearing them again probably is going to make you go, oh yeah, I remember that now. Hopefully that's the case. Okay, so we'll move on to doing a little bit of work with normal distributions. Okay, everybody, normal distributions. I'm just going to go through my standard stock slideshow for you. So normal distributions, a nice metaphor that I've used in the past is that it is a 3-headed dragon because it gives us 3 specific pieces of useful data about what you recall is a shape. Okay, remember that the mean, the median, and the mode are all the same value for a normal distribution. So if you're looking at any data set and the mean, the median, and the mode are all the same value, you know you're looking at what can be illustrated as a normal distribution, which looks like a symmetrical mound. Okay. Here it is, symmetrical. Resulting shape is symmetrical. Okay. Mean forms 0 point in the middle, 3 standard deviations on each side. Of course, we'll look at it in a minute. Okay. Outlying values are on both ends called the tails. Okay. There it is, tails. Approach but never quite touch the x-axis, which is the, of course, the horizontal line. Okay. Ooh, scary. The standard deviations. Yes. Okay. Let's take a look at this. So standard deviations, you remember these. Here's the 0 in the middle. To the right, we have the positive standard deviation 1, standard deviation 2, 3, and then to the left, that's important. I always ask these questions. I'm always asking these questions about recognizing the standard deviations to the left and to the right of the center line. If it's to the right, they're positive. If it's to the left, they're negative. Okay. Okay. And we know that there are specific values in between them. Okay. We know that the space between 0 and 1 is the same as 0 and -1. They are symmetrical. Okay. And percentages. Woo. Okay, it's percentages. Okay, we also remember this. This is always something I test on. Between -1 and +1, 68.26%. Between -2 and +2, 95.44%. We remember this from the class. And -3 and +3, 99.74%. Again, this is total review. And because it's symmetrical, the space between here and here, which is 34.13, which is just simply half of 68.26%, okay, is the same on both sides. Okay, symmetrical. Okay, there they are. I even had a slide in there for you. So it reminds you up here that between here and here, 68.26% of all cases on the normal distribution, and that half of that is on each side here. Okay, and you could do the same thing going all the way out. Okay, I like this slide. I like all these slides. Okay, ooh, percentiles. What are we going to do with those? Okay, remember we read percentiles from left to right instead of from the middle out. I'm going to repeat that right now so everyone hears me loud and clear. We read percentages from the midline out. Okay, we read percentiles from the left to right. So beginning on the far left, we're beginning with the 0 percentile all the way up to the theoretical 100 percentile. Okay, and basically, if you're at a percentile, you say that if I'm at the 50 percentile, 50% of all scores are below and 50% of all scores are above. And you can say right here, if you're at the 90, okay, you could say that 90% of all scores are below and 10% are above. That's how you read percentiles. It's like if a baby has a 20% birth, if a baby is on the 20th percentile for birth weight, you know that that baby has a birth weight score that is greater than 20% of all other babies for his, her, or their age, but then there's 80% heavier babies. Okay, that's how you read percentiles. Okay, you can see again, I just kind of did that for you. So again, we did percentiles. Okay, percentiles are in fact useful for us to gauge where any particular point is in a data set in relationship to all the others in terms of ranking. It's kind of a ranking question. Okay. Oh yeah, my favorite. Okay. I used to think that correlation imputed causation. Obviously, that's not the case. Then I took a statistics class. Now I don't know. Sounds like the class helped. Well, maybe. Remember, he can't assume causation, so he doesn't know if it helped. Okay. Bad statistics joke. Okay. Okay. Sorry about that. Always room for humor, right? Always room for humor. Okay. So we're back to where we were. We covered frequency distributions. I talked about the absolute versus the cumulative. Okay. Measures of central tendency, mean, median, mode. Talked about measures of variability or dispersion. They are, again, standard deviation, variance, which we're not really going to talk about. Standard deviation is simply variance with a square root. That's all that is. And then the range, which is something I could ask you about. Then we talked about the normal distribution values. We could say, again, normal distributions give us standard deviations. They give us percentages, and they give us percentiles. Those were the basics there. We read percentiles from left to right. We read percentages from the middle out. And we know that those percentages like 68.26 and 95.44, they're the same on every normal distribution. So if you're looking at a normal distribution, you already know what the characteristics are going to be. The next thing we would move to from here are z-scores. And I'm going to give you some problems with z-scores, but I'm not going to do it on this presentation. I'm going to do it most likely through Canvas on some written paper. So what I can do is I can give you the z-scores, you can work them out, and then I'll give you the answers and you can compare them. But probably not as appropriate to try to do that here, but I will do that. Okay, so that is going to do it for a presentation. I'm going to be I'm going to be writing out some questions to review for, or I should say more questions to review for exam number 4 if that's what you're looking to do. Okay, take care. Talk to you soon.